Nice. Some of the waveforms you already copied in the last class. You did not copy all these waveforms. Just I think the last two waveforms we need to copy, the D and as well as the E waveforms. Okay, let's get into this circuit operation. Right now what we are discussing, before we discussed the operation principle and construction of unijunction transistor along with the voltage current characteristics. So today's class we are looking into the applications of unijunction transistor. There are many applications on unijunction transistor. So one such application what we are discussing is a relaxation oscillator circuit which is based on the unijunction transistor. You can see here we have an unijunction transistor and this will work like an oscillator. Some of the today's batch they are experiment on the relaxation oscillator based on op-amp. But right now what we are seeing is going to be a relaxation oscillator based on UJT. Okay. So everything remains same except the device has been changed in our laboratory experiment, the fifth experiment. This was replaced with op-amp. Apart from that, everything is going to be same. The working principle what we are trying to explain today for relaxation oscillator remains same for op-amp based relaxation oscillator. Look at the various elements of the circuits. We have a resistor R2 which is attached to the here we have a terminal which is base B2 and base B1. You look at the original device structure of unijunction transistor. This is a base B1 and this is going to be the base B2 of the UJT transistor. And we have resistor R1. This is going to be of small value which we connected here. It's not large value here. And this, of course, this is going to be large value of resistor which we are connected here. This R indicates a resistance through which this particular capacitor keeps charging. Capacitor role here is to charge and discharge also. Okay, when you provide voltage to this, this will charge. When you don't provide voltage to this, whatever the charge it has been acquired, that will start discharging. That's the basic operation of this capacitor. Okay. The main role of this capacitor is to charge and discharge. When you apply some voltage, it will get charged. Okay, it will charge to supply voltage. We will see that in what path this capacitor will charge and in what path it will discharge. And you can see where the output has been taken. We are taking from the emitter terminal. Itself becomes an output for this circuit. Okay. So let's look at the operation of this one. So we have here supply voltage which we indicate as plus V. This is the DC supply voltage. And initially when you switch on this circuit, switch on the sense, if you turn on some power supply to this, what will happen? Let us see that. So this UJT will be in the cutoff region initially. You know that, you remember, just go back to the last class what we covered. Okay. Whenever the UJT is in cutoff, what current will flow in the UJT? Just look at characteristics and tell me. When UJT is in cutoff region, there will be leakage current will start flowing through this. Because now the moment you switch on this, initially at initial stage this will be in the cutoff region. Okay. Slowly what will happen is the capacitor present here will start getting the voltage from this. You start getting the current from the R and as well as take the voltage from this particular supply voltage and it keeps charging. So charging path is going to be like this. So this is nothing but capacitor charger. How long the capacitor can charge? Suppose if I apply 5 volts here, this capacitor can charge up to 5 volts. Practically speaking, it will not charge to 5 volts. It may charge to 4.6 or 4.5 volts. That's all. If you give, even though if you give here 5 volts. But ideal case, what we expect is if you apply 5 volts here, you want to be this capacitor to be charged up to 5 volts, but that never happens. If you give 5 volts here, this will charge up to 4.6, 4.5, 4.6. That's all. When it cannot go beyond 4.6, okay, because there is some drop occurs across this house. Okay, so you understand this how the capacitor gets charged here. This is going to be the charging path. Now here, also look at internal equivalent circuit of this. What are the elements present inside this UJT? You have a diode, PN junction inside this. Just recap the things we have covered in the last class. There is a PN junction inside this. There are two resistors inside this. RB1, RB2. Remember that RB1 act like a variable resistor, RB2 act like a fixed resistor. And inside this, at the emitter point, we have a diode, PN junction. Whenever this is in the cutoff region, what will be the status of this PN junction present inside this? It will be reverse passed. So look at here now. Once this capacitor gets charging, let's assume that this charges to the supply voltage. Voltage across the capacitor between this point and this ground becomes, say for example, plus V. Let's assume that a situation where in which capacitor has been acquired sufficient amount of charge across this now, the voltage has become now a plus V, which is same as this. Now what will be the condition inside the diode present here? Do you think it remains reverse biased? Remember again in the previous classes we said that there is a voltage which we call as peak voltage, which is equal to eta times VBB plus for the other fashion. It is a cut-in voltage, right? Remember this formula which we have given? That means whenever the voltage at this point exceeds this, diode inside this becomes power bias. Whenever the voltage at this point is less than this, diode present inside this will be reverse biased. Now here we have taken a condition from reverse bias to the power bias. Initially we will switch on the condition, switch on this power supply. This capacitor has no charge. When there is no charge in this has diode present inside this is reverse bias. There was some leakage flowing here in this part. But now let us assume that the condition where capacitor has been fully charged. Because you continuously keep giving supply for this, it has been completely charged through this path. Once capacitor charges, it behaves like a source. Of the system will act like a source. So from this source, look at inside this, there is a diode, PN junction. Voltage across capacitor, which is nothing but our VP now. Now this has exceeded this particular voltage. Okay. Now what will be the condition? Diode present inside this? It will be power bias. Once it is power bias, because this is power, diode present inside this is power bias because of this capacitor fully charged. So this will charge up to the plus V. Now this is will act like a source. Whatever source present here, the alternative source now here, because once capacitor fully charged. Now because of this, diode present here will be power bias. So once it is the power bias, this will act like a short circuit now. Now capacitor will start discharging now. Earlier it has acquired the charge through supply voltage. Now it will start discharging because this has been turned on. When this has been turned on, capacitor will start discharging through like this to the ground. It loses charges. It loses charge. How long this can lose charge? Again look at diode here. So as long as diode is okay, once your capacitor keeps losing charge, that means at this point voltage keeps reducing. Voltage keeps reducing. Okay, voltage keeps dropping. Okay, the situation will come where diode again will get reverse bias. Understand? Again will get reverse bias. Now this will act like an open circuit. Again capacitor will charge. It will charge to the plus V. And once your capacitor acquires charges, again diode becomes here forward bias. Once diode is forward bias, this acts like a short circuit. Capacitor will start discharging, and again capacitor keeps losing charge. Okay, when the point has been reached in such a way that okay, when capacitor has been charged, discharged, okay, such that okay, the diode becomes reverse bias. Again it will start charging. So what is happening inside this? Are you getting some kind of oscillations, charging, discharging? Same waveforms which you have plotted here. You can see now. Whatever the operation here present here has been shown. If you try to apply the waveforms at this particular point and as well as ground, you will get this kind of waveforms. See in this waveform, the first waveform, whatever it has been shown here, output waveforms, you can see that capacitor is charging. You can see the slowly it is charging because as I mentioned that this resistor is going to be very large and this resistor is going to be always very small. That's why charging happens slowly, discharging happens immediately. You can see charging late, charging is late because of more resistor value here. Because your charging time constant depends upon, suppose if I say T is the charging time constant, it depends upon resistance and as well as capacity. Typical formula is going to be 0.69 R into C. This is the formula for charging the capacitor. That means charging here depends upon the resistance as well as the capacitor value. Now not given a capacitor value, let's look at the resistor value. Resistor here, this is going to be large value because of this charging will happen slowly, and this waveform is this loop is nothing but which is the discharging loop. We mentioned here this is going to be discharging. This is a path which shows discharging capacitor. Capacitor discharge. You also identify the paths. Capacitor charges through the plus V, R, and as well as this particular capacitor. This is a charging path, and capacitor discharges through R. Because again, powers of current cannot go to the supply itself. Okay. Once this is fully charged, okay, so this will bypass this. This itself will act like a source. Now this has fully charged now. Now it can provide charge to the passive elements. Passive element is here is UJT and as well as resistor. Okay. So to keep providing charge to this. So once it keeps providing charge to this, the charge across this will keep on. Once it discharges voltage across this, it will keep on losing the voltage across this, and it may at one point basically where the diode gets reverse bias. Again this particular path is removed, and again capacitor will start acquiring charge from the supply. Discharging and discharging keeps on continuing. Same thing I mentioned here, this is going to be the charging path. Charging, look at here where it has been started with. It's a value voltage has been started with. How much it can charge? It can go up to VP. It cannot go beyond VP. And again look at this. Once capacitor is at this particular point, capacitor is fully charged. That means diode inside the UJT has been forward biased. Okay, that makes it now. Now what is happening here? Capacitor is discharging now. Okay, through the UJT and as well as R1. Capacitor is discharging. Okay, so discharging. At this particular point, what has happened now? Voltage across diode has been reverse biased. Okay, now again capacitor will start charging, discharging. So we are getting some kind of oscillations there. Okay, that's why it is called relaxation oscillation. You know the meaning of relaxation? Capacitor relax for some time, and again charges for some time. Charge, relax, charge, relax. Okay, in this operation, we are getting some waveforms here. So this is the one of the the application of UJT is called as relaxation oscillator. The circuit relaxes for some time because it does not need any power supply. Okay, this is going to be the basic operation of The frequency of operation of this circuit is given by this typical formula. For this, no derivation is needed. Just you have to remember the formula. Frequency of oscillation of this circuit is given by RC. You can see where is R and where is C. The value of this, the frequency of oscillation depends upon this resistor value as well as this capacitor value. So they are present in the denominator. And you can see ln, a natural logarithm here of 1 over 1 minus eta. Eta is nothing but intrinsic stand-up ratio. The typical value of this is 0.7, which we mentioned in the last class. Okay. So what about other waveforms here? We have showed other totally 3 waveforms here. This is you can see that the same waveform has been smoothened here by manipulating this circuit. What I am trying to do is, instead of using this resistor here, I will use a constant current source. Just a small change which I will do it for the circuit. You can rewrite. This is a symbolic representation of current source. If you represent the 2 circles overlapping, that indicates that it is a constant current source. Constant current source. That means if you make this capacitor to charge to constant current source like this, definitely you are going to get a smooth transitions here. You can see the difference between this waveform and this waveform. Charging is almost exponential. It's exponentially it is increasing, exponentially it is decreasing. Right? But here you look at here, this is going to be straight and almost. It's a linear kind of graph here because you are charging through the constant current source. Okay, this is nothing but a source which provides a constant current. Okay, it's very difficult to get this constant current source. If you have voltage source, you can derive this constant current source. We don't have any current sources available. We have a voltage sources available. Okay, you can see AC voltage available through the plugins. And if you want to have a current source of this type, you have to convert from voltage source to the current source. We assume that here this current source is going to provide a constant current. And the constant current is charging this capacitor. And because of that, we get it here a smooth transition. Okay. Exponential has been converted to the smooth transitions. Same thing you can observe here again. It almost looks like a sawtooth waveform. I have seen the teeth of the saw which we used to cut for wood. Almost the shape looks like that. So this kind of waveforms can be generated from the circuit by having a constant current source. And rest of the waveforms you can see that this is the waveform at V1 terminal. If you measure the through the oscilloscope between this point and the ground, you will get this kind of waveform. This is the waveform at V1 terminal of the same circuit. And waveform at the V2 terminal of the circuit, if you measure at this point and at the ground, you will just get reverse of these waveforms. You can see here the small pulses indicates discharging, and the large the pulse width indicates charging. Whereas here it's going to be reverse here. Large pulse indicates which is a charging, and small pulse which indicates here as a discharging. Okay. But this kind of pulses can be used in digital circuits to trigger the flip-flops or some Bari circuits also. Okay. So these are the examples of the waveforms. You take it across V1 as well as V2 terminal. So look at this. If you have any questions, remember this formula because problems will be asked based on this formula. We have one problem which we need to solve it on this problem. You can take up this problem. The UJT based relaxation oscillator circuit. The UJT based relaxation oscillator circuit. UJT based relaxation oscillator circuit. And the waveform observed across. And the waveform observed across capacitor. And the waveform observed across capacitor is shown in figure below. Is shown in figure below. So determine the intrinsic stand-up ratio eta. Determine the intrinsic stand-up ratio eta of the UJT used in the circuit also determine the time period capital T of the waveform, time period capital T of the waveform in bracket between there. Given that the forward bias voltage drop is 0.7 volts. Close the pipe. The forward bias voltage drop is 0.7 volts. This is the voltage drop inside the UJT. Okay, this is a diode. The voltage drop of that is given as 0.7 volts. You can take this circuit. Capacitor value is 0.1 microfarad. You can copy this waveform, also given, and the formula is available here. You can use that formula to calculate the frequency of oscillation. Now it is asked intrinsic stand-up ratio. Before you go to that, can you calculate eta for this? How do you calculate eta? You can use this formula for the calculation of eta. Since Vp from the waveform, which is 7.9 volts, you can use this formula. Vp is equal to eta Vpp, but instead of Vpp, which we take here as V, the V value is given as 12 volts. Eta V plus Belgaum. From this, I hope you can calculate the value of eta. Eta becomes which is Vp minus V gamma divided by eta. If I transfer this becomes a V. Now substitute everything and calculate what is V? 7.9 minus 0.7 divided by 12 volts. What's that? So punishment what given in the last after section. Switch on the mobile in the classroom. Get suspended, you know. What's the eta value? What about this? You are supposed to get 0.6. There is no unit for this, don't write any unit. From this you can calculate frequency of oscillation. RC is known, eta is known. You can estimate the frequency of oscillation, and from that you can estimate time period. Just substitute there and calculate the value of frequency of oscillation. So frequency of oscillation is 1 over RC. R is given as 10K, 10 into 10 over 3 into capacitor value is 0.1 microfarad, 0.1 into 10 power minus 6 into 1 divided by 1 minus 0.6. Work out this value and find out the frequency of oscillation. At what rate the oscillations are going. When this is calculated. and in turn we can calculate time reciprocal of the frequency. Frequency must be in terms of kilohertz or megahertz. Yeah, it's 1.09 kilohertz. All of you got this? Calculate the time period if the frequency is known, take the reciprocal of that. You are supposed to get the 0.92 milliseconds, 0.92 milliseconds. Go through this. If you have any questions, you can ask before we start with the next unit, which is effects. The syllabus for your first test is will be this complete unit will be there, and before the just the 2 days before whatever the syllabus we cover, MOSFET from the MOSFET, that can also be added. Any questions about this? And 10 times theory questions as well as problems also. Try to do as many exercise problems as possible. That's all. Any questions? Field effect or transistors. The examination sake you can expect 20 marks from this. Field effect transistors. This chapter is not so difficult. The main things which you want to remember in this chapter is basically few waveforms, few theory, a brief theory, and more of characteristics and device operation. Mathematical content is less in this chapter, so you can easily, without worrying about mathematical equations, you can start studying this. More of the theoretical and characteristics. First, let me define what is an field effect or transistor. This is going to be the hard trend today. Okay, field effect transistor. Previously, whatever we studied, the bipolar junction transistors are not using currently. Okay, you can see many research laboratories they are not using bipolar junction transistors. They are outdated already. They only accept some academic institutions. Research laboratories will not use these UJTs. But you can see that field effect transistor is widely used by many research laboratories, industries, okay, and even in academic institutions like you go for any abroad in Belgaum, MS. You will start with a course of microelectronics, where this will be the basic, basic element, which is going to be field effect transistor. Career starts from, if you want to become an electronic engineer, career starts from field effect transistor. We never teach, the bipolar junction transistor, just a basic foundation. Why we need to learn basic bipolar junction transistor is, if you understand the basic working of bipolar junction transistor, it's very easy to understand field effect transistor. So we'll just discuss this chapter particularly deals with more of the theoretical concepts of field effect transistors. The word itself tells you that these are the transistors which are based on the field effect. What do you mean by field? What is effect? How do you differentiate these terms? Field effect. You know the role of transistors. It can be used as a switch, it can be used as an amplifier. Same applications, whatever we said for UJT, is also applied here. But you can see that field effect in the sense you are going to establish some electric field. Are you aware of electric field? So if you have mobile handset with you, surrounding you there is an electric field which you are not aware of it. Okay, so nowadays you can see that the electric field is going to dominate because of high frequency usage. You see that you compare to old mobiles and current mobiles. In the old mobiles, you can see that there is some antenna which is coming out. And people, never use nowadays such kind of mobiles because it does not look good if you have antenna with your mobile. Just you can see the old mobiles, they have a piece of jack like antennas. In cardless phones also, you will see if you have in our home, they have some antenna which is the size of this jack, right? You know why the antenna size has been come down? Because of operating frequency. Now you see that present mobiles, there is no antenna at all. Antenna is there, but it is invisible for you. It is embedded inside the device itself. And think about operating frequencies, which is very high. Gigahertz frequencies, microwave frequencies, your mobile is operating. It's very dangerous. Even though mobile company says that you have taken a lot of precautions, okay, about the high frequency operations here, but never. So most of the mobiles, almost all mobiles, they are not taken any precautions for branded mobiles. Okay. So large frequencies coming out, radiations are coming out here. In one or other way, they are going to be dangerous for human beings. So as antenna becomes very, very less, operation frequency becomes more. Okay. As I told you, the typical operating frequency range is going to be in terms of gigahertz, microwave range, which is very dangerous for us. Okay, so we will talk about same kind of electric field. Through the electric field, this transistor is going to conduct. This transistor is going to work. So we will explain that how exactly the transistor works. How this is going to be very popular. If you look at the little history about UJT and as well as field effect transistor. Last week I was going through the inventor of bipolar junction transistor and inventor of field effect transistor. Actually, this was invented long back 100 years before. And BJT was invented nearly in 1947, which our independence came. Same year BJT was invented. Look out now, BJT is outdated, this has become popular. It was invented 100 years before, this became popular. BJT invented just, independence is celebrating 67 years for even BJT also. That has not become popular, outdated. You know, reason is what? Why it has been not become popular in between some few years? Because many people does not know about the importance of this. When publications has been come out, papers has been come out, people start thinking that when the concept of integrated circuit has been come out, ICs. The person who invented IC is going to be a very popular person who died long back. Jack Kilby is a chairman of Texas Instruments, one who invented the integrated circuit. Because of him, the FET becomes popular. Look at the change now. Before that, okay, this was invented in the 1960s. Till that, the BJTs were ruling the world. Almost all electronic devices were used by BJTs. This was not so popular. In 1960, Jack Kilby invented integrated circuit through the concept of cocoon silkworm. You might have seen. From that concept, he invented the integrated circuit. From there onwards, then people start thinking, well, if you put the BJT, what happens into the ICs? Lots of difficulties. You cannot manufacture BJT in integrated circuit form. I have seen BJTs available except few TTLs with lot of difficulties. Your TTLs also outdated. Very difficult. So due to that, but FETs putting in integrated circuit is very easy. Okay. Now people want, I know the large number of electronic components in the small chip. How it is possible? Without integration, do you think it is possible? You cannot make it. So they have started putting the field effect transistors into the integrated circuits. Now today you see that we can house even billions of components in the small IC, which is few millimeter square ICs. It is possible. All this is possible because of Jack Kilby. We should thank him. Nothing was possible. Anyway, is right already. Okay, because whenever the demand is more, people think that BJT is great. Okay, but difficulties arise, the thing that field effect transistor is great. And slowly we will introduce two terms here. One effect is also not great. There is something called CMOS, which has been derived from the field effect transistors. And that's also going to become outdated in another 20-25 years. Okay. Electronic is like that. Today, whatever the purchase, mobile will purchase it, tomorrow it will be the old. Day by day, new technologies will come. The same way, field effect transistor is basically the, let me give the a 3-terminal device. 3-terminal device. Whenever I say 3-terminal, you can imagine that even BJT is also 3-terminal. Emitter, base, collector. Okay. As if you look at BJT and FET, terminals are remain same almost, but namings are different, that's all. In case of here, we have terminal we have is source, we have a drain, we have a gate. Same as that. The role of the emitter is to emit the charge carriers, and collector is to collect the charge carriers, and base is to control that in case of BJT. However, in case of FET, there is a source which is similar to that of emitter, and there is a drain which is similar to the collector, and gate is going to be just like a base. That means current flow from the source terminal to the drain terminal is controlled by the gate. Interesting technology, right? You are controlling something. If you don't have control, device becomes useless. Something must be controlled. Okay. What you are controlling here? The current. How you are going to control? Applying some voltage here. Here it is different from the BJT. Right? That's what is called the field. How do you establish electric field? When a current flows through the wire, there is some electric field surrounding that. You can experience that way. Sometimes. Same here, when you apply some voltage to the gate terminal, that creates some electric field. Through that field, you can make the charge carrier. You can control the charge carrier movement from source to drain terminal. That's why I said it is interesting. You understand this? You are going to create some electric field, and from the electric field, you are going to control the current movement from source to drain. That means you can increase the electric field, you can decrease the electric field. That is possible. How do you increase or decrease? Again, by increasing or decreasing the voltage applied to the gate terminal. So this is going to be the basic background of field effect transistor. It is a basic 3-terminal device. Almost role of FET is same as BJT. Okay, later on, once we know the FET has been invented, almost all applications we were using the BJT that were replaced with field effect transistors. You see now in mobiles, we don't use BJT based amplifier, we use FET based amplifier. You see in the computers, we don't use BJT based switches, we use FET based switches. Reason is power consumption and even switching capability, everything is going to be very less in this. High speed switching is possible with FET. Even the BJT has got some good number of properties, especially in some there is a technology called as BiCMOS technology, where we combine bipolar and as well as CMOS technology. That is not used in today's. Again, there is a lot of drawbacks in that. People have studied even mixing technologies also. A lot of the advantages are not seen. Due to that, we have seen that only field effect transistor is going to serve you better, because this can be embedded into the integrated circuits. So coming to the classification of FETs, let me classify classification. How do you classify the FETs? FETs can be broadly classified into 2 types. Among them, the first one is going to be the junction field effect transistor. The junction field effect transistor, shortly we call this one as JFETs. The other category is going to be the MOSFETs, the metal oxide semiconductor field effect transistor. Shortly we can call this one as MOSFET. Okay, this is the way you can classify the field effect transistor. In turn, this MOSFET can be classified further into the enhancement mode, enhancement MOSFET, and other one is going to be depletion MOSFET. And this classification has been made depending on the construction, based on the construction and mode of operation. Okay, the FET can be classified into the JFETs and as well as metal oxide semiconductor field effect transistors, you can call as MOSFETs. And even you can see that among these two category of FETs, we are using MOSFETs is going to be very popular. Among the two different types of MOSFETs, depletion is not quite popular. Enhancement MOSFETs are going to be most widely used in many applications. Okay. The different categories are there. The first thing here is we need to give difference between BJT versus FETs. You can do it next. But later on you can have a device structure of junction field effect transistor and the types here, and again here the types of the MOSFETs here. We have again here N channel and P channel MOSFETs are there, which you can discuss it later on. First you can take a class bipolar junction transistor versus field effect transistor. Difference between BJT versus BJT and FET. First column we can make it as BJT. Second column we can make it as FET. This is usually asked for 5 to 6 marks examination. BJT versus FET, 5 to 6 marks. You can at least write 4 to 5 differences in this marks. The first one is BJT is a current control device, whereas FET is a voltage control device. I can write mathematically like this: IC is a function of base current. This is the mathematical I am expressing it. As I said that BJT is a current control device, whereas FETs are the voltage control device. You can see here also we can write mathematically VGS. You can see that what I have written here is IC is going to be the collector current in bipolar junction transistor. IB is the base current. The collector current is a function of the base current. This shows that it is a current control device. That means to control the collector current by varying the base current. This is going to be mathematically you can express it like this. What about here in case of FETs? You can see ID is nothing but the drain current and VGS is nothing but the gate source voltage. And you can control this drain current by applying suitable gate source. That's why this is called as voltage control device. Next is going to be FETs are bipolar device. Bipolar device, whereas this is going to be FETs are unipolar device. What do you mean by bipolar device and unipolar device? Both electrons and holes are responsible here for the conduction. If you want to make the current flow here, is responsible is because of the electron movement and as well as holes movement.